Sir, you are muted.
Oh, sorry, sorry. So before starting this basics of probability, I have to say the application of probability theory in other fields also. So although probability is the branch of mathematics, but it has wide of application in other fields also, like in finance and physics, artificial intelligence, okay, biology, and various subjects. There are many applications of probability theory, and particularly in computer science, there are various domains where you can use this probability theory, uh, like in data analytics, machine learning, discrete mathematics, information security, and artificial intelligence. These are the various domains where you can use, you can find the application of probability. So experiment, first, what is experiment? An experiment is a process of measurement or observations. Okay, so any process of measurement or observation is known as experiment. And so it may be in laboratory or in factory or on the street or in nature, anywhere. That is the process of measurement or observation is known as experiments. And random experiment, an experiment E is called a random experiment if it satisfies the three conditions or 3 points here. Uh, the first one is all possible outcomes of this experiment E are known in advance. Okay, all the possible outcomes will be known in advance. The first point. Second, it is impossible to predict which outcome will occur at a particular trial. So here trial means the single performance of an experiment. Okay, a single performance of an experiment is known as trial. So second point is it is impossible to predict which outcome will occur at a particular trial. And third is E can be repeated under identical conditions for infinite number of times. So for example, if you take one example, then it will be very clear to you. For example, for tossing a coin, okay, for the if we consider an experiment tossing a coin, then uh, the outcomes we know all the outcomes. You can say that it will be either head or tail. Okay, they are the possible outcomes. So these outcomes are already known in advance for tossing a coin. This experiment, okay, is the point one. And point two, it is impossible to predict which outcome will occur at a particular trial or at a particular performance of an experiment. That is, for tossing a coin at a particular trial, we cannot say surely. That is, we cannot sure that what outcome will occur at a particular trial. That is, we cannot say that exactly head will occur or exactly tail will occur at a particular trial. Okay, so this is the point two. It is impossible. You cannot predict that which outcome will occur at a particular trial. And third, E can be repeated under identical conditions for infinite number of times. That is, you can repeat this experiment infinite number of times. That is, you can toss 5 times, 15 times, 20 times, any number of times you can toss. So this is the 3 points of random experiment. If any experiment satisfies these three conditions, 3 points, then we say that the experiment is random experiment. So tossing a coin, throwing a dice, these are the examples of random experiment, and inspecting a light bulb, that is either it is defective or non-defective. So these are the examples of random experiment. So next, sample space. The sample space is the set of all outcomes of an experiment. Okay. A set of all outcomes of an experiment is known as sample space, and it is denoted by S. So for example, for tossing a coin, the outcomes are head or tail. So here in this case, the sample space S equals to 1, a head or tail, H comma T. Okay. And next, what is event? An event is a subset of the sample space S. and we denote event by capital letter like A, B, C. Okay, and these A, B, C are subject of the sample space S. So an event is a collection of outcomes contained in the sample space S. So and it is called simple event if it consists only one outcome, and compound event if it consists of more than one outcomes, the 2, 3, 4 like this. So for example, for this random experiment like rolling a dice. So these are the examples of random experiments. Their outcomes and some events are defined here. Okay, so rolling a dice. So for rolling a dice, the outcome set of all outcomes is 1, 2, 3, 4, 5, 6. Okay, so if you you can define these two types of events like A and B. Suppose A is odd numbers and B is even numbers in rolling a dice. Then A, the elements of A are 1, 3, 5, and the set elements of B are 2, 4, 6. Okay. And obviously here A is already contained in S and B is also already contained in S. So A and B are subset of S. That is, the event is a subset of the sample space S. For another random experiment, inspecting a light bulb, uh, just to examine it is defective or non-defective, then the sample space S is defective and non-defective. This. So next we see what is the classical definition of probability. So as we have already studied this probability and how to find the probability for a particular problem in 10 plus 2. So I think all of you know what is the definition of probability, classical definition of probability. So can you say what is the probability of the event A? Suppose A is the sample space and A is any event in S. Then how to calculate probability of A? What is the definition of probability of A then? Anyone?
Sir, it is the random chance. Sir, it's not random. It's a chance of some event happening or not. For some
Yes.
event to be true.
Chance of event is true, like in but what is the actual definition? If we suppose A is the sample space and A is
A by S.
okay, I'm suppose actually we see the number of points or number of elements in this sets A and S. Okay, so suppose number of points in the sample space S, that is total number of points for a particular random experiment, is n. Suppose n, small n, and number of points in A is m. Then we write this probability this. Okay, probability of A equals to number of points in A divided by number of points in S. That is m by n. If we denote the number of points in A by m and number of points in S by n, then probability of A equals to m by n. And probability of S, clearly probability of S, and clearly probability of S equals to 1. Here S is the sample space, so if we find probability of S, just follow this definition. Number of points, probability of S will be number of points in S divided by number of points in S. That is, in that case, m equals to n. Then probability of S equals to 1. Okay. So also from this m by n, you can conclude that probability of A always lies between 0 to 1. Okay, the probability of particular event A is always lies between 0 to 1. This follow from this definition. Okay. For example, probability of A equals to m by n. So here m and n, m is number of points in A, number of points in S is n. And we know that an event is subset of S. So obviously this number of point in in A is less than equals to number of point in S. That is m less than equals to n. This is clear. M less than equals to n. So if m less than equals to n, then m by n less than equals to 1. So probability of A less than equals to 1. Okay. So also number of points here, probability is number of points. We count the number of points in these events A and S. So number of as we count the number of points, so this number of points cannot be negative. So m and n is always uh, greater than 0. So this probability of a is greater than equals to 0. Okay. So probability of a is always lies between 0 and 1. Here is the example how to find the probability using the definition. So in rolling a dice once, what is the probability of A? That is event A, where A is obtaining 5 or 6. And what is the probability of B? B is the event that even numbers. So for rolling a dice, this set of all outcomes, that is the sample space, A is 1, 2, 3, 4, 5, 6. And A is the event obtaining 5 or 6. So A containing the element 5 and 6, and B is even number, so 2, 4, 6. Then probability of A, number of points in A divided by number of points in S. Number of points in A is 2, so 2, and number of points in S is 6, so 2 by 6, 1 by 3. Similarly, probability of B, number of points in B divided by number of points in S. Number of points in B is 3, and number of points in S is 6, so 3 by 6 half. So mutually exclusive events. Next, mutually exclusive events. Two events A and B are said to be mutually exclusive events if they have no common points. That is, if we find the intersection of these two events A and B, then A intersection B will be always phi. If phi is a null event. Similarly, for infinite number of events A1, A2, A3, if AI intersection AJ equals to phi for I not equals to J, then we say that these events are mutually exclusive event. So if A and B are mutually exclusive event, then their intersection is always phi. Okay. So for example, here for this problem, here A equals to 5, 6 and B equals to 2, 4, 6. So if we find A intersection B, then A intersection B equals to
6.
6. So this is not phi. A intersection B is not phi. So A and B are not mutually exclusive events because they have common points. But if we define A as even numbers and B as odd numbers, then A intersection B equals to phi. Then we say that A and B are mutually exclusive events. Next, axioms on or basic properties of probability. Uh, so we've already seen this. For any event A in the sample space S, probability of A is lies between 0 to 1, and probability of S for sample space S, probability of S equals to 1. And for mutually exclusive events A and B, for two mutually exclusive events A and B, that is for A intersection B equals to phi, probability of A union B equals to probability of A plus probability of B. Okay. Similarly, for A1, A2, A3 dot dot, for these various numbers of events which are mutually exclusive, probability of A1 union A2 union A3 union dot dot, this equals to probability of A1 plus probability of A2 plus probability of A3. So these two formulas follows only if these events are mutually exclusive event. Okay. Then complementary event. We denote the complementary event or complement an event of A by either A dash or A superscript C or A bar. These are the notation of complementary event. Okay. And the complement of an event A is a set of all outcomes in the sample space S that are not contained in A. Whereas complementary event means other than A. The elements that's already contained in A, we remove that from the sample space S, then the remaining elements will be in complementary in the event in the complementary event, that is A complement. So in some books, this notation union, in place of union, they use plus notation, that is A union B and A plus B are same. Okay. And intersection, like A intersection B and AB, these are same. Okay.
Sir,
Yes.
sir, I couldn't understand the above line P of phi 0 equal, sorry, P of phi equal to 0 where phi is the null event. Sir, what is a null event and what does that line mean?
Null event means there is no point in that event phi, no outcome. Okay.
So phi is a event which has zero probability.
Yes, zero.
Uh,
Because no element, so then in that case m will be your 0. In this definition,
sir,
m will be 0. Then probability of phi will be 0.
okay, sir.
Yes. From this follows. Probability of phi is 0 by n, so 0. Now more probability properties. Now I'm going to prove some properties of probability. We have to remember these properties also, because in 2.2 or chapter 3, we use these formulas directly to find the probability.
Sir, you provide the notes or we have to write it?
No, I will provide this PDF file. Okay, I think I have already uploaded this uh,
Oh, okay,
PDF
sir.
file in Google Classroom. Yes.
Oh, sorry, sir.
So after the each class, I will upload this PDF file in Google Classroom. Now I am going to prove this some properties of probability. So this is 2.1 to 2.2. Theory part of 2.1 and 2.2. So I think all of you know the Venn diagram, how to so the Venn diagram for sets or events. Okay. For example, for any two events A and B, is A union B. For A union B, the Venn diagram is like this. This whole portion of A and B. Suppose this is A set and this is B set for event A and B. Okay. And intersection, like this portion. Okay. For this set A and B, this is the A intersection B. Okay. And A complement, suppose this is your sample space, whole set of all outcomes. Okay. And this is your A set. Okay. A set means this. So outside A, this will be your A complement. So except A. So now we use this Venn diagram to prove some properties of probability. The first one, for an event A, probability of A plus probability of A complement, this equals to 1. Okay, probability of A plus probability of A complement equals to 1. From which you can write probability of A complement equals to 1 minus probability of A. Okay, 1 minus probability of A. So for any event A, probability of A plus probability of A complement equals to 1. To show this. So suppose this is your S whole sample space and this is the event A. Okay, this is the event A, and this outside your is A complement. This is A complement. So from this diagram you can write A union A complement. What will be A union A complement then?
S
S whole sample space, and A intersection A complement
phi.
phi. Okay. So from the second relation, that is A intersection A complement equals to phi, you can say that these two events A and A complement are mutually exclusive events. Okay. So now if we take probability from both sides, so this is probability of A union A complement equals to probability of S. Okay. Now since A intersection A complement equals to phi, so this implies A and A complement are mutually exclusive events. Okay. And we have already seen in axioms of probability that if A and B are mutually exclusive events, then probability of A union B equals to probability of A plus probability of B. So now since here A and A complement are mutually exclusive events, so left hand side is simply probability of A plus probability of A complement. We have also seen that probability of S equals to 1, so this equals to 1. Simply from here you can write probability of A complement equals to 1 minus probability of, this is proof, probability of A complement equals to 1 minus probability of A. So now we see one example. We use this formula, that is probability of A complement equals to 1 minus probability of A, that is how to use this complementary event to find the probability. So for example, suppose 5 coins are tossed. Tossed simultaneously. And find the probability of A. PA, where A is the event that at least one head turns up. Okay. At least one head turns up. Suppose 5 coins are tossed simultaneously, then find the probability of A, where A is the event at least one head turns up. So we use this complementary event to find this probability. So what are the total number of outcomes for this random experiment? 5 coins are tossed simultaneously. Can you say the number of
2 to the power 5.
2 to the power 5, that is 32. Okay, so for 1 coin it is 2, for 2 coin again 2, for 3 coins and 2 to the power 3, 4 coins 2 to the power 4, and 5 coins it is 2 to the power 5. So total number of outcomes is 32.
So 31 by 32 answer.
Yes, 31 by 32. Now can you say if A is at least one head turns up, then what is the outcome in A complement?
All tail.
All yes, all are tails. So that means this is T T T T T. This only one outcome in the event A complement. All are tail. This is the complementary event of A. So then you can easily find this probability of A complement. This equals to number of points in A complement, that is 1, divided by number of points in S, that is total number of points, that is 32. Okay. And then using this formula, that probability of A plus probability of A complement equals to 1. So probability of A equals to 1 minus probability of A complement. So this is 1 minus 1 by 32. So this is 31 by 32. Okay, so probability of at least one head turns up is 31 by 32. Second property, if B subset of A, okay, then show that probability of B is less than equals to probability of A. Okay, probably if B is subset of A, then probability of B less than equals to probability of A. So again, you can take the help of Venn diagram. So since B is subset of A, so B that is B contained in A, so we can draw this Venn diagram for these events A and B. Suppose this is A and this is B set. Okay. And in between this A and B, so this portion, this is actually A minus B, A minus B. Okay. So you can write this event A as A equals to B union A minus B. You can write this A equals to B union A minus B. Okay. Now take this probability from both sides, then the probability of A equals to probability of B union A minus B. B union A minus B. So right hand side is probability of B union A minus B. We know that if A and B are mutually exclusive event, then probability of A union B is probability of A plus probability of B. See here A and A minus B, this, sorry, B, B and A minus B. B and A minus B, these two events are mutually exclusive events. So because if we find this intersection B, A minus B, so this is phi. These are mutually exclusive events. So you can write this equals to probability of B plus probability of A minus B. Since B and A minus B are mutually exclusive events. Okay. So from this, probability of A minus probability of B, this equals to probability of A minus B. Okay. So again, you know that for any event A, probability of A is always greater than equals to 0. So here probability of A minus B is always greater than equals to 0. So this implies probability of A minus probability of B, this is greater than equals to 0. So this implies probability of B is less than equals to probability of A. Okay, probability of B less than equals to probability of A.
Sir, can we say for any two events, PA minus B equal to PA minus PB?
For any, repeat please. Yes.
Sir, for any two events, can we say PA minus B equal to PA minus PB? Or should it should be only with a subset of A? Then only we can say that.
Yes, only if B subset of A. Okay.
Not always.
Not always. Yes.
Okay, sir.
Also, you are able to write this because these are mutually exclusive event. That is, their intersection is phi. Otherwise, you cannot write this. Okay.
Okay, sir.
Hence, probability of B less than equals to probability of A. Next, third property. Uh, show that probability of A intersection B complement is equals to probability of A minus probability of A intersection B. Probability of A intersection B complement equals to probability of A minus probability of A intersection B. For two events A and B, so suppose this is event A and this is event B, this is A and this is B. So then this portion is A intersection B, and this portion is, what will be this? Can you say this first left hand, this white portion?
B minus A intersection B.
B minus A minus B. First one.
Sir, B minus A intersection B. Sir, the right one.
Minus A intersection B.
Huh?
So the right one is B minus, the left one is A minus.
Yes, exactly. So this is A minus B. So A minus B means A intersection B complement. Okay. And this is A intersection B complement. Similarly, this white portion under the circle, inside the circle, this is B minus A means B intersection A complement. Okay. So we have to prove this. So here probability of A is present. So we try to write what is A, event A. Okay. Using this set of events. So A equals to A is the union of this A intersection B complement and A intersection B, right? So A equals to A intersection B complement and union A intersection B. You can write this. Okay. Now take this probability from both sides. So this is probability of A, and again this A intersection. See this A diagram. A intersection B complement and A intersection B. These two events are mutually exclusive events. Okay, so we can write this as probability of A intersection B complement plus probability of A intersection B. Okay. Since A intersection B complement and A intersection B are mutually exclusive events. So from this we can write probability of A intersection B complement. This equals to probability of A minus probability of A intersection B. Okay. Probability of A intersection B complement, this equals to probability of A minus probability of A intersection B. So is it clear this properties 3? How to come it? Any doubts in this 3? Properties 3?
No, sir.
So another properties here for finite mutually exclusive events, that is finitely many mutually exclusive events like A1, A2 dot dot up to AN. Probability of A1 plus A2 plus dot dot plus AN equals to probability of A1 plus probability of A2 plus dot dot probability of AN. So you can prove this using mathematical induction. Okay. That is for n equals to 1. It is n equals to 1. This is trivial. Obvious. That is for n equals to 1 means only one event. So probability of A1 equals to probability of A1. For n equals to 2 also, probability of A1 plus A2 equals to probability of A1 plus probability of A2. Since A1 and A2 are mutually exclusive events, then assume that this is relation is true for n equals to m. Then you have to show this is also true for n equals to m plus 1. Okay. So this is very easy to prove by using mathematical induction. And next, then for any event A, probability of A less than equals to 1. I have already shown this, that probability of A less than equals to 1, that is using the definition. Or otherwise you can also use this property 1, that probability of A plus probability of A complement equals to 1, and we know that probability of A complement is always greater than equals to 0. So this follows that probability of A less than equals to 1. Okay. And then for any two events A and B, probability of A union B equals to probability of A plus probability of B minus probability of A intersection B. So this is homework. You have to prove this formula. Actually, it was in 10 plus 2. So please try to prove this. Probability of A union B equals to probability of A plus probability of B minus probability of A intersection B. Okay. And then for three events also, the formula is probability of A union B union C equals to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C plus probability of A intersection B intersection C. Okay. So using this for two events, that is probability of A and B equals to this, you can easily prove this for three events. Okay, by assuming that any two events like B or C as considered as one event, that is B union C is considered as one event, then you can take the help of this formula for two events. Then you can easily prove this.
Sir, can you send these notes?
Yes, yes. I have already uploaded this note in Google Classroom. You can download it from there. Okay. So this was the theory part from 2.1 and 2.2. Okay. So in next class we will discuss some problems from exercise 2.1 from the textbook. Okay. So I am taking attendance. Roll number 1,
Present, sir.
1026,
Yes, sir.
1058,
Yes, sir.
111,
Present, sir.
134,
Present, sir.
119, 119, then 206,
Present, sir.
1235,
Yes, sir.
1246, 1253,
Present, sir.
1268,
Present, sir.
1315,
Present, sir.
1397
Sir, 1348.
is 1348.
Present, sir.
Okay. Okay. So actually I have program from 2 p.m. today, so some program. So okay, I'll mark all present for today. Okay.
Okay, sir.
Okay, you can leave.
Okay, sir.
Thank you, sir.
Thank you.
Thank you, sir.